town to Philadelphia like a train. And when those Philadelphians saw him, they set up a wail, for they thought that he must really be old Halley's Comet Tail. And they won't know who it really was for months and months and months. No, they won't get wise to who it was for months and months and months. I bought an aeroplane myself and I'm going to fly it once, but I may not get out of the hospital for months and months and months. Now all you married gentlemen should bless the hobble skirt. I'll show you how to tame your wives if you are real alert. In case you come home late at night and wifey makes a roar, just pick her up and spread her out upon the parlor floor. And I don't think she'll get up again for months and months and months. No, I don't think she'll get up again for months and months and months. You can go back to your club and enjoy yourself for once, and your wife will stay just where she's put for months and months and months.
My man's on the ocean, bobbing up and down. He belongs to Uncle Sam, but he's always on my mind. Girl, take a tip from me.
I was down at the depot to make my getaway, and Providence being against me, it proved to be too late. I tried to play off insane, but found it would not do. The people all against me, it proved to make no show. Judge Coxey passed the sentence, the clerk he wrote it down. On the 30th day of June to die I was condemned. My name is Charles Utah, my name I'll never deny, to leave my aged parents to sorrow and to die. But little did I think, while in my youthful bloom, I'd be carried to the scaffold to meet my fatal doom. My sister came in prison to bid her last farewell. She threw her arms around me, she wept most bitterly. She said, my loving brother, today you must die for the murder of James A. Garfield upon the scaffold high. My name is Charles Utah, my name I'll never deny, to leave my aged parents to sorrow and to die. But little did I think, while in my youthful bloom, I'd be carried to the scaffold to meet my fatal doom. And now I mount the scaffold to bid you all adieu. The hangman now is waiting, it's 2:15. The black gout is o'er my face, no longer can I see. But when I'm dead and buried, dear Lord, remember me. My name is Charles Utah, my name I'll never deny, to leave my aged parents in sorrow and to die. But little did I think, while in my youthful bloom, I'd be carried to the scaffold to meet my fatal doom.
a courting and he did ride. King Kong, kitty, kitty, kai-me-yo, with a sword and a pistol by his side. King Kong, kitty, kitty, kai-me-yo, kai-mo-kee, kai-mo-kee, way down yonder in a holler tree, an owl and a bat and a bumblebee. King Kong, kitty, kitty. He rode till he came to Miss Mouse's door. King Kong, kitty, kitty, kai-me-yo, and there he knelt up on the floor. King Kong, kitty, kitty, kai-me-yo, kai-mo-kee, kai-mo-kee, way down yonder in a holler tree, an owl and a bat and a bumblebee. King Kong, kitty, kitty, kai-me-yo. He took Miss Mouse up on his knee. King Kong, kitty, kitty, kai-me-yo, and he said, little mouse, will you marry me? King Kong, kitty, kitty, kai-me-yo, kai-mo-kee, kai-mo-kee, way down yonder in a holler tree, an owl and a bat and a bumblebee. King Kong, kitty, kitty, kai-me-yo. Miss Mouse had suitors 3 or 4. King Kong, kitty, kitty, kai-me-yo, and there they came right in the door. King Kong, kitty, kitty, kai-me-yo, kai-mo-kee, kai-mo-kee, way down yonder in a holler tree, an owl and a bat and a bumblebee. King Kong, kitty, kitty, kai-me-yo. They grabbed Mr. Frog and began to fight. King Kong, kitty, kitty, kai-me-yo, in that holler tree 'twas a terrible night. King Kong, kitty, kitty, kai-me-yo, kai-mo-kee, kai-mo-kee, way down yonder in a holler tree, an owl and a bat and a bumblebee. King Kong, kitty, kitty, kai-me-yo. Mr. Frog hurled the suitors to the floor. King Kong, kitty, kitty, kai-me-yo, with his sword and his pistol he killed all 4. King Kong, kitty, kitty, kai-me-yo, kai-mo-kee, kai-mo-kee, way down yonder in a holler tree, an owl and a bat and a bumblebee. King Kong, kitty, kitty, kai-me-yo. They went to the parson the very next day. King Kong, kitty, kitty, kai-me-yo, and left on their honeymoon right away. King Kong, kitty, kitty, kai-me-yo, kai-mo-kee, kai-mo-kee, way down yonder in a holler tree, an owl and a bat and a bumblebee. King Kong, kitty, kitty, kai-me-yo. Now they live far off in a holler tree. King Kong, kitty, kitty, kai-me-yo, where they now have wealth and children 3. King Kong, kitty, kitty, kai-me-yo, kai-mo-kee, kai-mo-kee, way down yonder in a holler tree, an owl and a bat and a bumblebee. King Kong, kitty, kitty, kai-me-yo.
Old Enoch, he lived to be 365 when the Lord came and took him back to heaven alive. I saw the light from heaven shining all around. I saw the light come shining, I saw that light come down. When Paul prayed in prison, them prison walls fell down. The prison keeper shouted, redeeming love I found. I saw the light from heaven shining all around. I saw the light come shining, I saw the light come down. When Moses saw that a burning bush, he walked it round and around. And the Lord said to Moses, you's treading holy ground. I saw the light from heaven shining all around. I saw the light come shining, I saw the light come down. Dry bones in that valley got up and took a little walk. The deaf could hear and the dumb could talk. I saw the light from heaven shining all around. I saw the light come shining. I saw the light come down. Adam and Eve in the garden under that sycamore tree. Eve said, Adam, Satan am tempting me. I saw the light from heaven shining all around. I saw the light come shining. I saw the light come down.
Welcome to Driven by Me and Jesus. Tonight I will talk about the behavior tree in Unity, but I will go over at first for the description of a behavior tree. I did work with behavior trees in my course in Unity, and I can give some advice. The one I will pick for my game will be a specific one that I suggest, but I will go over many other behavior trees. So let's go. Will unmute my desktop because we will watch some videos. So the first time I worked with behavior tree, it was this one in Unity. It's Mono Behavior Tree. It's a visual scripting tree. You can make C#. I will check with you, but first thing first, let's watch. I need a refresh a bit because it's been a while, but I'm pretty sure I'm not so rusted. So let's watch
Thompson,
this.
and welcome to AI 101, the series that explores the artificial intelligence tools and techniques used in video game development. In the first entry of this series, I looked at the navigation mesh, a data structure commonly used in 3D games to enable AI characters to move around an environment, recognise obstacles, and make decisions about how to get from A to B as fast as possible. In this video, I'm looking at one of the core AI technologies that is now pervasive throughout much of the AAA video games industry: behaviour trees. While the wider world is caught in the thrall of machine learning, the games industry is heavily reliant on behaviour tree techniques. Now, I first explored how behaviour trees are used in my video on Halo 2, the game largely responsible for their proliferation, but since then regular viewers will have noticed how frequently they pop up. They've since resurfaced in my videos on Alien Isolation, Far Cry 4, Bioshock Infinite, Spec Ops: The Line, Far Cry Primal, Halo 3, Tom Clancy's The Division, and that's just the games I've elected to talk about on the show. So in this episode, I'm going to address what these systems are, how they work, how they're integrated into commercial game engines, and, from my perspective, discuss why they're becoming increasingly more popular in games and why as a developer and designer, you might be more inclined to use them. So first up, let's cover the fundamentals. What is a behaviour tree and how does it work? A behaviour tree is a data structure in which we set the rules of how certain behaviours can occur and the order in which they would execute. The term tree is denoted given that it follows the traditional rules of the tree data structure in computer science, meaning as a series of nodes that start at the root, which is this one here at the top, which is then linked to other nodes by connections. Now, in fancy computer science terms, this is actually a directed acyclic graph, meaning it's a collection of nodes that are connected to one another, but in each case there is a fixed direction and that it doesn't loop back or repeat itself. The logic of the tree works its way down from the top to a specific set of one or more nodes where a specific behaviour is going to be executed. A node that has been linked to by another one above it calls that node its parent, and any node it links to below it are called its children. And that's some good ComSci knowledge you're going to need to remember right there. Now, how a behaviour is selected within the tree is based on how it moves down through it and the nodes it executes. Nodes are typically found to be one of 4 types. First up, there's the root node. That's the one at the top. It has no parent, only ever has children, and it's where the execution starts from. Next up is the basic node of a tree called a leaf. This is where we actually put AI behaviours, such as running to a fixed position in the world, shooting an enemy, interacting with an object, stuff like that. It's the opposite of the root, can only have parents, and it has no children. After this we have composite nodes. These are special nodes that control the flow of how we move through the tree. And there are 2 commonly found composite node types. A selector, where it decides which child to execute based on some logic in the world. So for example, if the player is too far away, it won't execute the child node that does a melee attack, but it might decide to use a gun and shoot at you from range. Secondly, there's the sequence node. This allows us to execute several child nodes in sequence one after the other. This is great, say if you have a character that's under fire and you want it to run towards cover, then hide behind it, then take a shot at the player. Given that's arguably 3 distinct child nodes you're going to execute in a sequence. Lastly, there are also decorator nodes. These take existing logic of a child and manipulate it. This is great for making us repeat actions a certain number of times, or make a selector make a decision based on the inverse of the logic that we've given to it, and so on. So already with this setup, you could come up with trees that mash up multiple behaviours, like say deciding whether to have an AI shoot from nearby cover, rush in to attack the player up close, or stand their ground. And with this tree that I've mocked up here, it's easy to start visualising this design and subsequently implement it. Alright, so with the basics down, let's explore how they work and some of the cool features they carry. So traditionally, when behaviour trees were first devised, the idea was that every frame of a given game, the system would run an update from the root called a tick. The system then burrows down into the tree to find the node that is active, rechecking whether other nodes should be active along the way down. However, that's a bit expensive, especially when the tree starts to get really big. So nowadays, the tree will retain a reference to the active node and have that node process the tick. If it eventually finishes the behaviour at that node, then the tree will reevaluate what to do. In addition, a concept advocated by the Halo franchise was to make them more event-driven, meaning that the tree can quickly switch out of a given node to reevaluate which node it should be executing now based on an event occurring in the game world. Now, on top of all this is an additional component known as the blackboard. Blackboards are used to store useful data that the tree uses as part of the behaviour of multiple nodes, target locations, distances to nearest items of interest, even things like status variables like if the character is under fire or they've already executed a specific behaviour. The blackboard not only allows us to store this information to minimise the need for repeated calculations, but also you can use the same blackboard across multiple active behaviour trees. This makes it easier for different AI characters that are all using behaviour trees to share information, like where the player is, for example. It's a common one, you're going to use it a lot. For those keen to experiment with making their own AI that uses behaviour trees, the toolchain found in Unreal Engine 4 is arguably the best fully available tool out there to use. Pretty much everything I've explained.
Yeah. Also, I did use this a lot in Unreal. I did dialogue tree. I used the behavior tree to. There is a tutorial on YouTube. You search dialogue tree in Unreal using behavior tree. There is a guy who shows how to use it. Of course, everything that is graphic visual scripting like this behavior tree, you can do a behavior tree in code without visual assistance, and it is most likely faster, but of course it depends. You need to say it is faster. I need to do test and prove that it's faster. So it depends on the code. If the code without visual scripting is not well done, it can be slower. But if both are really well done, sometimes the visual scripting is slower. Unreal is known to have many visual scripting and being slower with their visual scripting. I don't know at what point they are right now. I've seen a GDC, I think, not long ago, a guy from Unreal. I'm not sure it's the GDC, but he said it was getting fine to script. I don't remember well, but they are still slower. There are still things that are slower, and the build, you need to include it in the build. Sometimes it's problematic, especially in Unity. Sometimes it's hard to understand when you start for the first time. Your build, you need to build your game every time you do something to check if it works the same. And when you do a behavior tree, the interface might give you some challenge interface with the build. So where was that? I use it for I want to be just real. Where am I? Am I okay? I'm dev. No, my usual. Dev. Unreal behavior. The dialogue tree. Not this guy, not this guy, not this guy. It's Ryan Riley. It's a very good tutorial to make a dialogue tree. It's for your dialogue with the NPC, or the player and the NPC. So press E and then you have a dialogue with the answers you can pick. So just so you know that you can do that. The one I will use, the behavior tree I will use, it's not. It might not be this one. I might script it if I find something. But we use the tutorial in my last project in school, and we use this one.
This is how AI optimizes.
It's a Unity Create Behavior Tree using UI Builder by the Kiwi Coder. So, no, not on this channel. I think I'm already subscribed on my other. So it's two part. The second part doesn't have the same name, but it's AI 11, AI 12, part 2. This one just he start with the visual. So the visual he has is a behavior tree that goes from left to right. But if you do the part 2, it will show you to do it from top to down. I think, if I remember well. I might use this for my behavior tree, but we will check today what we can find in code. This one we used the first time. It's fine. It's really fine. I could be using this one too. I might. It's possible that I would use it to save time, because this one you need to build it in code by yourself. The thing is, once you have it, then you have it. You can you have it for a long time. You can bring it on other projects, but you need to update it. That's the issue. You need to do the update yourself. It might be an old version of Unity. Then you would need to find out if there are missing things. But usually it's not that hard. 6,000. Okay, this guy, he says he used Unity 6 and it works like a charm, so it's still working. It's 4 years old now. It's still working. But if you create it, and then later, like 3 years later, you want to reuse it in new version of Unity, it's possible that you have like some issues and you need to repair it. This one, it's getting old. At least there's a 5-month update here, and we will search later on for what is new. Maybe there is something coming from Unity. So I will take a little break right now and come back in a few minutes. I forgot my Twitch. So see ya.
does Lisa learn choreography so fast?
Like, my desktop is like unmuted everywhere, so you may hear the mute his name. Just to short about Lisa dance memorization. Okay, that way I will be able to.
Explained thus far is implemented in the same fashion in the UE4 tree system, and you can get up and running with it pretty quickly. Now, a common question that arises is why would you use behaviour trees versus the likes of, say, a finite state machine? Data that the tree uses as part of the behaviour of multiple nodes, target locations, distances to nearest items of interest, even things like status variables, like if the character is up and running with it pretty quickly. Now, a common question that arises is why would you use behaviour trees versus the likes of, say, a finite state machine, which we've seen in my videos on the likes of Doom and Arkham Asylum.
The reason why, okay, so the finite state machine is similar to a behavior tree, but it's more like a round. You may have like an idle state, and everything revolves, go back to the idle state, or a state that is like a phase state, where the AI go back to a basic state. The issue with this compared to a behavior tree is that when you want to do when you want to make an AI that is complex, you will end up with this real huge mess. Let's see if we can see. Mess. Oh. My muscle memory is dyslexic. So this is not a mess, this is simple. Let's spaghetti. My god. Who's touched my spaghetti? Who touched my spaghetti? Wait, Martina. Yeah, that looks like this. That looks like this, like huge games. You want to make it their AI. It could be like, yeah, could be a joke, but I think it can happen. So the solution is a behavior tree. Can I add a little panel on my light? I think it's fine with without the panel. But, maybe a bit too light. And this one, maybe it could be more like this. Okay. So So the issue that it's that it will end up really hard to handle to manage, because it will be very huge and going like back and forth. The difference with the behavior tree is that the behavior tree will go always like a, I don't know if you say that in English, percolator, percolate, percolator, percolate, percolate, a liquid or gas filter readily through a porous surface or coffee at preferred percolate per. What does idea percolate mean? Does percolate means to think? It means thinking about an issue in no. Percolation is a pressure of a liquid slowly passing through a filter. So it's like it starts from the root and it goes down, which make it like less messy, because you don't go back like at certain point. You do go back, but it's more like going back one branch and going other branch. You always like, it's always going like the root down, then a branch, then it checks the leaf and go back another leaf, and then it goes back, and then it restart at the root. It restart at the root, and then it restart at the root. So it avoids doing like a finite state machine will do it will have a basic state like roaming, and then it will see a monster fight, go back to roaming, see something else, go back to roaming. But if you do like many interaction, will become really, really big, and it will be like a spaghetti. There is no like other route than the middle, so it makes like lines that goes like in every sense, instead of like a tree that goes only in one way. And it's harder to correct if there is a bug. So this is a finite state machine. You can mix, you can have a finite state machine that handles the animation, but it's activated in the behavior tree. So like your character would be animated with FSM, a finite state machine, but its action would be directed by behavior tree.
Or even something like planning, which is used in First Encounter Assault Recon. So let's discuss some common issues that can arise and why many developers adopt behavior trees as their method of choice. First up, let's consider how streamlined the flow is. Users can clearly watch the decision making happening in a top-down fashion from root to leaf. This makes for a more scalable system, even as the tree gets bigger. We can still follow the train of logic that gets us from the root down to a specific behavior. This visual readability is so important as the number of unique paths increases. Even in this shot taken from my case study on The Division, which was simply a visualization to imply the overall scale of the system, you can still kinda read the flow of it. Conversely, a finite state machine becomes a nightmare to follow the more complex it becomes and more connections are made between states. And this gets me to my second point.
I didn't remember.
By streamlining the logic, they're not only more designer friendly, but perhaps more critically, they're easier to debug. The combination of simplified flow, modular behaviors, and shared knowledge through the blackboard reduces the capacity for error, and it also resolves so many of the major issues a designer would have in building behaviors. By comparison, finite state machines are typically very code intensive. given the conditions of their execution are often tied to the code of that specific behaviour in that state. And even in the more recent implementations, such as Doom 2016, those state machines were built by programmers on request from designers. Meanwhile, many modern behaviour tree systems better support workflows where designers can quickly build new behaviours using modules already built with a program.
That's why you do visual scripting. It's if you go for this one, I might not go now that I think about it, because I want to go fast. I might pick this one, but I will see. But if you want to go for this one, keep in mind that the visual scripting that you will build, it's only for your non-programmer, your level designer, and as such, because it's a tool for others to manipulate script-like things easily, because it's hard to learn programming. It's faster to make a tool, to take a programmer in your team, make this tool for the level designer rather than teaching coding to your level designer. But faster than that, this is already done. You don't need to do it, you just need to install it and read the documentation how to use it. Okay, so I think I will remove this and then go back.
And only then pester them for specific bits of behaviour they might be missing. The third valuable aspect is reusability. We typically build individual behaviours in these trees such that they can be used in different contexts, and the logic of the tree will allow us to reuse the same node whenever we need it. Conversely, with finite state machines, many of the states are typically tied to that specific context, so it gets a little uglier the more you try and maintain them. Lastly, there's the big issue that impacts every AI system in a game regardless of scale: the CPU power and memory required to execute. The optimizations of tick processing and event-driven overrides have enabled behaviour trees to become more optimised over time, whereas a finite state machine still needs to update, typically every frame just to check it's in the correct state and conduct state transitions accordingly. Lastly, the use of blackboards help keep memory to a minimum, given it allows for data to be shared across nodes. The optimizations of tick processing. The third valuable aspect is reusability. We typically build individual behaviours in these trees such that they can be used in different contexts, and the logic of the tree will allow us to reuse the same node whenever we need it. Conversely, with finite state machines, many of the states are typically tied to that specific context, so it gets a little uglier the more you try and maintain them. Lastly, there's the big issue that impacts every AI system in a game regardless of scale: the CPU power and memory required to execute. The optimizations of tick processing and event-driven overrides have enabled behaviour trees to become more optimised over time, whereas a finite state machine still needs to update, typically every frame just to check it's in the correct state and conduct state transitions accordingly. Lastly, the use of blackboards help keep memory to a minimum, given it allows for data to be shared across nodes, as well as different AI all executing the same behaviour tree. Now, while this episode is dedicated to explaining how effective behaviour trees are, this isn't to say that they're the one and only option for crafting behaviours in your games. If your behaviour logic is relatively small and simple, finite state machines are more than sufficient for your needs. If you need something dynamic and reactive, planning is also well suited in a number of circumstances, but it often means the problem scale needs to be compact. Otherwise, the overheads of the planner could prove overwhelming, especially as the number of characters using the planner for decision making increases. Ultimately, it always comes down to the project you're working on and a lot of the smaller facets of the game's design. Alrighty, I hope this helps you better understand the theory of how behaviour trees work. As I say, they're incredibly popular in the games industry, and you can expect them to continue to crop up in future case studies when I'm exploring the AI of AAA games. Behaviour trees were the most voted for topic by my supporters over on Patreon. If you have a topic you'd like to see me explore next on AI 101, let me know in the comments. But
Good morning, good afternoon everyone, and welcome to this Unity tutorial on how to create a simple behavior tree in less than 30 minutes. In this episode, we're going to implement a very simple guard AI using behavior trees to have it patrol or target and attack monsters. Are you ready? Then let's dive in. In a previous video, I talked about finite state machines, aka FSMs, and I discussed how this pattern can help you implement well-organized and well-structured behavior systems, as long as this behavior isn't too complex. In a follow-up episode, we saw how hierarchical finite state machines can mitigate some of the downsides of the FSMs by introducing inheritance and higher-order abstract states. But the fact is that when you try and model a more complex behavior, FSMs will eventually come short. Chances are that if you work on a really advanced AI system, or just on a player system that offers more options to the player, FSMs will be too rigid a structure to be pleasant to use as developers. Now, of course, you can always manage to cram up all of your super AI in an FSM, but trust me, it will soon be a real pain to maintain, verify, and update. So another common AI pattern that is way more flexible is the behavior tree. Here, rather than defining a finite set of states that your character can transition between, you define a tree of nodes that altogether create branches with various behaviors. Each node has an execution state that determines whether it's currently running, if it's succeeded, or if it's failed. This state is computed by evaluating the node, thanks to a function that's naturally called evaluate. The state of the branches is then computed from the state of the children nodes and aggregated in various ways depending on this parent node type. The nodes at the very bottom that have no children are called leaves. And those leaves are going to contain the actual checks and tasks that are performed by our AI, while the rest of the tree is the logic structure that's going to essentially switch from one behavior branch to another. In other words, the inner nodes control the flow, and the leaves ultimately implement the actions. The flow control nodes in the middle define how the tree is processed. They can be of two types. Those structural nodes can be composites. So those nodes are sequences that have a bunch of child nodes that they run in predetermined or random order, one after the other or in parallel. Usually they act like an AND or an OR logical gate, for example. Or else those structural nodes can also be decorators. In that case, they have a single child and they may impact its processing or modify its results before returning, like reversing the failure success state, delaying the execution, and so on. Action nodes are more diverse, but you can usually group them in two categories: the checks and the tasks. Checks are simple if-like nodes that condition whether or not this branch is valid and should continue. Tasks are more complex nodes that perform a real update of the character or its environment. Something really nice with behavior trees is that prioritizing actions is easy. Because the success of the child nodes conditions how the branch and therefore the tree runs, combining composite ANDs and ORs can directly give you a set of prioritized features. Behavior trees natively handle sequences, interruptions, and fallbacks. Also, as you can see, this structure is pretty easy to read and to visualize. You just follow the branches by priority and at each node check whether it succeeds or not to know if you can continue on this branch or if you must go to the next one. But the biggest advantage of behavior trees is that they are highly modular and scalable. By removing or adding a branch, you essentially add or remove a feature to your character. Similarly, it's pretty simple to copy a sub-branch and paste it somewhere else to just copy-paste part of your behavior. Some subtrees can even be completely self-contained autonomous bits of logic that you can then re-import and reuse in another character's behavior tree to quickly implement chunks of a system, like following a target, patrolling between a set of points, etc. Moreover, this modularity means that you can build your tree piece by piece and have an incremental design strategy. Finally, note that contrary to finite state machines, where by definition states are as isolated from each other as possible, behavior trees are far more flexible to leaking information between nodes. Even though each node is executed on its own and lives its own life, it is pretty common to have some shared data state that can be accessed from various points in your tree to have global, although context-specific variables. But enough talking. Let's get to actually coding a behavior tree so that we better understand how it works. In this tutorial, we will create a basic AI for this guard. By the end of the session, it will be able to patrol between a set of points when idle, keep an eye out for monsters like this skeleton, and go to them if one is nearby to finally attack until the monster is dead. We'll focus on the guards, so the enemy won't do anything, but of course the techniques we'll learn here can be applied for any unit, so you could easily transpose what we're gonna do to another AI system for the skeleton. For this tutorial, I'll be using various free assets from the asset store or from online texture databases. You can check out all the links in the description for more info. And I won't go into the details of how I made this 3D scene, but if you're interested, be sure to let me know in the comments and I might make another video on this topic. Okay, so let's assume you have your 3D scene designed, populated and ready. In here I have my guard, the skeleton near a campfire with a simple particle system, and a few crates and lights for the ambience.
Foundational video about game AI, and it's going to cover the essentials of behavior trees so that we can dive deeper into topics such as Blackboard architecture and a few code, and it will contain a lot of the things that we need. The first thing that every node needs is to be able to report on its status. So in the behavior range of our children, we're still going to return running. That part's not any different. Order they were added to the parent, but in some sort of
The quantum computer, they're calling it,
can compute many times faster than the current breed of supercomputers.
Today we're going to build a shared data store known as a Blackboard. We're going to divide and conquer today, so the first part will be about building the Blackboard that can otherwise but in some sort of
Le Kia Sorento, nouveau look
impactful AI behaviors you can use in your game projects. This is a beginner-friendly C# and Unity tutorial. We'll see how to make enemies follow a player character, make line of sight, simple 2D pathfinding so characters actually avoid obstacles, a patrol behavior, and even a sneaky shoot and retreat creature. Remember that we also have 5 quality game dev courses on Udemy. Each teaches you how to make art, sound, and code for different game projects, from a platformer adventure to a fun online multiplayer arcade experience. So if you like our teaching style, consider giving those mega courses a look. Links are in description. Alright, so let's start off by creating our first enemy AI, which is this basic follow enemy. So he'll just follow the target around and stop once he reaches a certain distance to him. So I've got an empty C# script attached to our enemy character. Let's now open it up and I'll show you how to code this simple behavior. Let's start by creating our variables. So we're going to need a public float variable for the speed of our enemy, as well as a public transform variable for the targets that we want him to follow. Lastly, we'll make a public float variable called minimum distance that will be used to stop our enemy once he gets close enough to our targets. Now, to make him follow the player, there is nothing more simple. We just need to go inside of the update function and set our transform.position to be equal to vector2.moveTowards. This function takes in 3 parameters. The first one is the starting position, so we will put in our current position, so transform.
Hey everyone! Has the name inside the parentheses?
All 6 of you have been invited to compete.
A top-down RPG using content from the Unity Asset Store. Our goal for this video is to bring our enemy characters to life with AI. For this project, we'll be using Behavior Designer, a behavior tree creation tool by Opsiv. First, what is a behavior tree and how can it help us? Is to bring our enemy characters to life with AI. For this project, we'll be using Behavior Designer.
Good morning, good afternoon everyone, and welcome to this Unity tutorial on how to create a simple behavior tree in less than 30 minutes. In this episode, we're going to implement a very simple guard AI using behavior trees to have it patrol or target and attack monsters. Are you ready? Then let's dive in. Good morning, good afternoon everyone, and welcome to this Unity tutorial on how to... Good morning.
Если вы интересны very good morning to all of you. Today we are going to discuss the topic strips. Let's go through the contents. These are the contents which we are going to discuss in our presentation. Firstly, we'll talk about the topic what is strips.
Is strips language.
But of course, for us the most interesting aspect is the adoption of planning within the game. As has been discussed at great length on this channel, Fear's major contribution is the introduction of planning AI. Planning is a concept whereby an AI system can take a look at a problem and start to plan out actions in advance. It seeks to find a series of actions that, when applied in sequence, will achieve a long-term desired goal. The AI of Fear is heavily inspired by STRIPS, the Stanford Research Institute problem solver, first devised in 1971 by Richard Fikes and Niels Nielsen. But despite it being over 30 years old, it had yet to be considered in the context of games. The final system, as previously mentioned, is dubbed Goal-Oriented Action Planning, and subsequently had a huge impact on the AI for video games.
The block code problem.
Hello. Language for planning AI problems. And in this video, we are going to learn what is strips language and the action schema of strips language with some examples. The action schema of strips language is also same as the general action schema, which we have seen in the last session. If you don't know, please see the previous planning problem video. And now let us go to the video. What is strips? The Stanford Research Institute problem solver is an automated planning technique used to find a goal by executing a domain from the initial state of domain. With strips, we can first describe the world. How we are going to describe? By using initial state and goal state, by providing object, actions, preconditions, and effect. So here we are using two categories of terms. First one is state and second one is action schema. States, we know initial state and goal state are there. Initial state is the starting state of environment. Here variables and functions are not allowed, so we can use only the direct data. And in the action schema, objects, actions, precondition, and effects are there. Objects can be derived by variables. And by using variable, we can do actions, and precondition and effects also we can use variables. That is, in the action schema, we can use only the variables, but in the states, we should not use any variable. Once the problem is described, that is, the agent problem is described, then we can provide the problem set. The problem consists of an initial state and goal condition. Strips can then search all the possible states, starting from the initial one, executing various actions until it reaches the goal state. The next one is planning domain definition language. It is a common language for writing scripts domain and a problem set. Here most of the codes are English words, so it can be clearly read and well understood. So it is very much useful to write a simple planning problem of artificial intelligence. The next one is
In the previous lecture, we put together our selector and we got to a point where we could get our character to move towards our doors. Now, at this stage, it's not the behavior tree letting us down. Well, there's nothing really letting us down at the moment, but it's not the behavior tree that we need to manipulate to fix the movement position of our character, but we have to extend the methods because we've got a behavior tree, but we're also trying to interact with a nav mesh. And whatever you're doing in whatever type of game you've got, you're going to be interacting with the game environment itself. So you're going to have a code that kind of links behavior tree stuff to the actual game. Now, if it was an animated first-person shooter or something like that, then you would have to have a whole bunch of your own methods that call animation states and things like that. But in this case, we're really only concerned about nav mesh states and moving the nav mesh. Now, if we go back into our robber code, this is the highest kind of level of the behavior code. This is the stuff that you want to write in here that interacts with your behavior tree. Once you've created your behavior tree structure like we've got, you shouldn't have to go in and touch that. You don't want to put any specialty nav mesh code inside of your behavior tree. It should be very generic that you can apply it to anything. So we're going to come back into our higher level.
Good morning, good afternoon everyone, and
Other tools keep you guessing about your team's progress. With Motion, I get instant visibility. Who's overworked, what's behind, and exactly where we stand. Here's how it works. You enter a new project with its deadline, urgency, and estimated time. Boom! Motion automatically carves out time slots in your team's calendar, ensuring they complete the work well before the deadline. Unexpected meeting or last-minute client request? No sweat. Motion instantly readjusts your team's schedule, keeping all projects on track. It's like having a personal assistant for your entire team who never sleeps, minus the coffee runs.
When it comes to game AI, making the right decision can get complicated fast. It's easy to say that when a sim is hungry, they should eat. But what if they're both hungry and bored? Which need should they satisfy first? And considering there are multiple ways to satisfy each need, such as making a meal versus ordering pizza, which specific action is the right choice here? Or what if all of their needs are reasonably satisfied, so they don't have anything that needs immediate attention? Rather than stand and stare into space, they should do something. And in a combat encounter, even a modest engagement might leave a unit with several options that all seem decent on the surface. Should a unit run up to an opponent to deal strong melee damage but risk exposing themselves, or should they hang back in cover and opt for a weaker ranged attack? And how should their current health and ammo impact this decision? It's a lot to figure out, and a simple state machine or behavior tree with some extra if statements really won't cut it here. The situations your AI can find itself in are just too varied and murky. At best, you'll have something extremely predictable and therefore both boring and exploitable. At worst, your AI just won't work how you want it to. This is where utility AI can be useful. Utility AI tries to answer the question, what's the best action I can take right now, by allowing for objective comparison between actions that can be as similar or as different as the game demands. This objectivity comes from assigning a normalized score in the range 0 to 1 to each possible action an entity can take in that moment, and then selecting the action with the highest score for execution. This score is typically referred to as the action's utility, hence the name for this technique. We use the term utility because how useful that action is will depend on the game state in that moment. A melee attack may always do a lot of damage, but if no enemy is within range to attack, then it has no utility to us because we can't actually apply that damage to anything. Conversely, if an enemy unit is right next to us, is low on health, and is weak to our attack type, this melee attack is now extremely useful.